All right, welcome back. We will have class 4 today, importing and combining data sets. Today is a magical day for you guys because so far you've been working with data sets that we have cleaned and generated for you. So while it's nice for learning activities and for learning purposes, really the power comes with being able to import your own data and then thinking about how to clean that data, visualize that data, and so on. So today we'll be going over a package called readr, which Akshay will give a lecture on. He'll also mention combining data sets. So this is something that Paul Grimsrud likes to do, thinking about aligning two different data sets using a VLOOKUP. So this is the equivalent of a VLOOKUP for you, Paul. And then Ali will finish the day by talking about a package called stringr, which is specifically designed to work with strings or character vectors and querying things inside of strings. So do you guys have any questions before we get started? All right, then Akshay, the floor is yours. This is our studio.
Okay, cool. Thank you. All right, so today, like Matt said, we're going to do like a live demo of going to a website, choosing a data set, downloading it, and importing it into R. So we do that once we've downloaded the data set. The readr package within Tidyverse has a range of functions that enable you to import various types of files into R. And they're all of the format read_**. So it could be a CSV if it's a comma-separated file, or TSV if it's a tab-separated file. So I'd like you to, oops, there's, right. Just go to uniprot.org, which I'm sure everyone here knows about. And once you're there on the home page, if you go to the Swissprot, so the one that the database that contains manually curated protein information, and for this example, just so that we don't have a giant data set, we'll just select human, but you could select whatever organism you like. And Uniprot has some default columns there. If you don't want those columns, if you want to select information that you're interested in, you can just click on columns, which is what I did here. All right, I did that. And if you scroll down, Uniprot has an incredible amount of information, like sequence information, gene ontology, PTMs. But for this example, just in the interest of downloading something relatively small, I'm just going to choose protein names and protein length. So not very interesting, but just an example. But you can choose whatever you want. And once you've selected the columns of interest, you can just hit save. And now if you scroll down, oops, you'll see it's been updated. If you're happy with this and you want to download the dataset, just click download. And Uniprot allows you to download this file in various formats. For today's class, we can just do it as a TSV, a tab-separated file. But as you can see, you can do it in Excel, plain text, and so on. And I just leave it as compressed, which is the default, and you just hit go. Oh, I should have said, please follow along using the 04_student RMD file.
Which form did you download it in?
It should go into your downloads folder.
Yeah, but which form did you download it in?
Oh, tab separated. So it looks like it's completed downloading. And to get a dataset from your download folder or wherever it's downloaded to into our Studio Cloud, just go here and click the upload button. And then choose File, navigate to your download folder.
Can you do that one more time?
Sure. I think I need to ask Map where the download folder is. Just click Upload here. And then choose File. Sorry, Matt? Matt? I can't see your download folder.
What an easy thing to do. In a Mac, it's pretty easy. If you have a download here, you can just drag it, and then it will find it. So just navigate. I mean, you guys usually have a downloads folder somewhere when you download something from the internet. So this is just an example of one way to get something from the internet or a data set. But remember that since we're using RStudio Cloud, you have to put it into your cloud environment. If you weren't using RStudio Cloud and you're using a local installation of RStudio, you also still have to know where it is. In most cases, you need to put it into your working directory. So we'll sort of gloss over that just a little bit right now, because really what we want to do is just have the file that you just downloaded in the same directory as is the R Markdown document. In this case, it's a cloud, so that's why we have one extra step to upload it.
All right, does everyone have their downloaded file in this folder?
Can you show us what your downloaded file looks like when you download it?
Like up here?
Yeah, well, like, can you open it?
Sure.
What are you curious about?
Mine just doesn't look big, so I think I'm missing something.
Oh, it might not, if you just open it up like that, it might not look good, but when you import it, you can preview it. You can preview it just to see if you have the right columns. So if everyone has the downloaded file in this folder, what you can do is you can either just type out the commands, or in this case, there is a shortcut. Sorry. If you just go to Import Dataset up here in your Global Environment tab, and since we're using the readr package, you go down to From Text readr. And all you have to do is browse, click on Browse, and select the file. So in this case, we saved it in for miscellaneous. See, it's here. And once you get there and select it, all you have to do is click Open. And down here in this code preview chunk, that's all the code you would have to type out if you wanted to do it yourself without having to click on different things. Now you can see in the data preview, everything isn't just one column. That's because the default delimiter, the default separator for readr is comma, but it's not comma separated, it's tab separated. So all you have to do is change this comma to tab. And now you'll see I just selected 2, and then Uniprot gives you the default entry. So mine only has 3 columns. And this looks nice. I hope it looks nice for everyone. And if it does, all you have to do is click Import. And you have a new data set. And you can use this, as we did in previous classes, using dplyr or ggplot. Importing stuff can often be the most difficult thing you do, but once you get the details down, it's super straightforward using the readr package.
When you were picking the file, it said file/URL. Does that imply you can download stuff directly from it on that?
Exactly.
So just go to the mitochondrial database and just
You could do that, yeah. So, as Paul said, another thing you can use readr for. So this is just the this is an example of if you had a file just named uniprot.tsv in your working directory. All it takes to import it into R, and when you import something, you have to assign it to a new object. So in this case, I just called it uniprot. You would just do read_tsv, and then open close brackets, and within the brackets, you would put the name of your file in inverted commas. And this is basically if we didn't have to download anything and we had a file called uniprot.tsv, this is all you need to do to import it into R. And that's the output. As Paul mentioned, you can use the readr package to import data from a URL. So as an example, there's this series run by this person who works at our studio called Tidy Tuesday, where they tweet out a publicly available dataset, and that you can download from this person's GitHub page, and you're encouraged to use that to make plots, and then you tweet that out with the code. So that's a really nice way if you type in hashtag Tidy Tuesday. That's a really great way to see what people are doing with the same data you have, and also how they did it. So that's a fun thing to do. And a few weeks ago, I guess months ago now, they had one on pizzerias in Manhattan. So all you would have to do to import that data set into R would be, and that was a CSV file. So I just have the URL here, and I think if you go to your code, the appropriate code chunk, and just hit play, you'll now have a pizza data set in your global environment, which we won't be using for anything, but it's there. So that's a simple example of how, yeah.
I have a question.
Yeah.
So whenever I was downloading my file from the
Uniprot?
Uniprot database, I ended up with the .tav file.
That's fine. That's
Okay.
tab
Is
separated.
that equivalent?
It's equivalent.
Okay.
Yeah.
Okay. Thank you. Is there how would we determine which file type we want?
What do you mean? Like usually it's when a colleague sends you something, they'll usually send it to you in whatever format they use. So R is quite versatile. It can deal with pretty much anything that is commonly used.
Okay. I guess then my question is, how would we determine which file size we prefer?
Whatever you prefer. So, for example, Uniprot gives you the option, if you prefer Excel, to download it as an Excel. I just find that tab separated is the most economical. So I was just doing that in the interest of downloading it quickly.
Yeah, I might also add, I try to stay away from XML. The way that XML files are parsed sometimes is a little complicated, but I think it's more rare to see the opportunity to download TSV or CSV or Excel, or so most of the time it's like, here's the data, right? So it's not often that you are able to choose. We're just using Uniprot as a test case. So here's one example of a publicly available resource you can go to and easily download data, but you still want to get it into R. In this case, you use a readr package.
All right, so that covers importing. And if you have any questions about this and want me to show it to you again, just let me know. So the second part of my talk today is about combining data sets. So previously, everything we've spoken about has been involved using just one data set at a time. But sometimes you're interested in combining multiple data sets, and this is known as relational data, because in this case, you're not interested in the specific data set, you're interested in the relation between two or more data sets. And if you, to do this in R, again, we'll be using the dplyr package, and the dplyr package contains a range of so-called join functions. So it's an alternative to using the word combining. Instead of combining data sets, you join data sets. And if you've ever used SQL, the logic of dplyr is identical to the logic of SQL. It's just that the names are slightly different. this is, so as a motivation for why you would want to do something like this, let's say you got a proteomics data set from Paul and you're understandably excited about it, and you want to get corresponding information for the proteins that you have in the mitochondria data set. So let's say you only wanted to filter in those proteins that are in the mitochondrion. Then you would just do a join between those two data sets, and then your new data set would give you relevant information for the proteins you're interested in. So this is a nice figure that summarizes how joins work. Now, in today's talk, I'll be covering just these 4 joins, but there are other joins and other ways to combine data sets. These are the 4 most common ones. So in this example case, you have 2 very simple data sets, A and B. They both have 2 columns. I should have said, in order to join 2 data sets, you have to have at least one variable in common. So in the example of getting a proteomics data set from Paul and joining it with mitochondria, you'd have to have, for example, a gene name variable in both. So the first join we'll be discussing is the left join. So in this case, if you wanted to join A to B, there's only one common variable, and that's x1. So you have to, so the syntax for all joins are the join, open brackets, the first data set, comma, second data set, comma, and then you specify what variable. Now in this case, you could get away with not explicitly stating the common variable because there's only one in common. But it's good practice to state by what variable you want to join 2 data sets. And the left join works by, so it matches only those rows in B that are found in A. And the resulting outcome is a new data set with 3, in this case, 3 columns. x1 and x2 from A with all the rows from A, and then the x3 column, but only those variables for which the match the ones in A. So in this case, you see x1 in B, dataset B, has an A and a B, which matches the A and B you see in A, dataset A. But dataset A has a capital C in the x1 column, which isn't there in B. There's a D. So when you left join, the D and T, that row, is discarded. But R has to put something in the cell, the corresponding to the C row. And since there's nothing from B, it just puts NA. So just to reiterate, the left join, so this is from the Tidyverse help page. So it will produce a new data set that has all the rows from A and all the columns from A and B. And the rows in which with no match in B will have NA values in the new columns. And if there are multiple matches, in this case, in the toy example I've shown you, there aren't multiple matches, but if there were multiple matches between A and B, all combinations of the matches are returned. So if you go to your, so for today's talk, we'll be using, once again, the proteins and mitochondria datasets to join on. And if you scroll down to that chunk, so you load your data. And if you take a look at proteins in mitochondria to see what is if there is a common variable, you'll find that gene name in proteins and symbol in mitochondria, they both contain gene IDs. So they contain the same kind of information, but they have different names. So to deal with that, this is the syntax you would use. So left join, open brackets, the name of the first data set, which is proteins, then the name of the second one, mitochondria, and then you state what variable you're joining on. So in this case, since gene underscore name, and symbol have the same data, they both have gene IDs. You can say, oh, I'm telling R that they are the same kind of variable. So you do that by saying by equals lowercase c, open brackets, gene name equals symbol. Now, if they had the same name, if there were a gene name column in both, it'd be simpler. You would just say by equals, in quotes, gene underscore name. Now, if you were to just run that left join, you would get the output in the console. But we would like to inspect it. You would presumably like to save the resulting data set. And to do that, you assign it to a new object. In this case, I just called it pmLeft. And once again, for people who didn't attend the talk on Tuesday, for the talk itself, for the slides, I pipe everything into a head function just so that I can see the first row. If I didn't do that, it would be it wouldn't look as nice, or it would be messier. So if you run that code chunk, it takes a little while, you will now see a new data set called pmLeft. And this one now has information from both proteins and mitochondria. And you can tell that because you now see you have many more columns than either of the original data sets. So this is a new data set. So that's the left join, so there's a book that Matt mentioned called Art for Data Science. And in their join chapter, they recommend that you use a left join as a default because you don't lose any information, or rather you don't discard any information. So the next join we'll be discussing is the right join, which you can kind of think of as the inverse of the left join. So again, the syntax is identical to the first one. You right join your first data set, in this case A, with your second data set, in this case B, by a common variable, in this case x1. But the difference between the left join and the the right join is you now see, again, you have the columns, the first two columns are from B, and you have a new column x2 from A. You have all the rows from B retained this time. In the previous case, it was all the rows from A and only matching rows from B. In this case, it's the opposite. It's all the rows from B and only the matching rows from A. And since there's no in x1 for B, there's a D, but in A, the x1 column doesn't have a D. So there's nothing to match. So it's just an NA. Now, as an exercise, I don't have it here, but I'd recommend going back at the end of the talk or whenever and changing the order. So right now we have the order as join proteins mitochondria. See what happens when you do join mitochondria proteins, and try to see if you can notice those differences and match them to the differences you see here. So again, this is just text that I took from the Tidyverse help page.
Actually,
Yeah.
So
Yeah.
the difference between right join and left join seems to simply be switching positions
Correct.
A and B in the code, right?
Yeah.
So you could have the same effect simply by switching the order.
Yes. You have the exact, but that would be a nice exercise to see. Confirm for yourself if that's the case.
sometimes, actually, you might have something like the gene symbol that's in, like, in Unify, you download there's a definition line that has like the species name of the protein, and then the gene name is under GN equals.
Yeah.
And then you might have another database where that's its own column. Does
Right.
that make sense? So before joining them, would you first parse that out?
Yes.
Okay.
Yeah. You'd have to get it into the same format, which
So they're exactly.
Ali's talk is about.
Yeah, following up on both of your questions. So Paul, yours first quickly about if your column doesn't have, the column contains information, but it contains other information. There's a useful function called separate in dplyr where you can carve out part of it. Ali will also teach you about string match or string detect or some of the stringr functions where you can pull out parts of a string if you have a longer string of characters. So that's absolutely possible. But you're absolutely right. You cannot join on a column that just contains information. It has to be the information, because the join is actually asking a very simple question: does this cell essentially match this one? It has to match it equally. It can't actually have any white spaces, trailing white spaces, or leading white spaces. So that's important. Keith, your question was about this left-handed join versus right-handed join. And one other important point to remember, the reason to have a right-handed join, because you might just say, oh, well, why don't you just flip around, like Akshay suggested, the order in which you list these. But remember, we oftentimes will find ourselves deep in the middle of a pipe of functions where we take a data frame and then we mutate it and then we do a couple of things and then we want to join it. So what you can then do is you might need that right-hand join in that string of functions rather than a left-hand join. The alternative would be to stop that pipe, to start a new one that's just a left-hand join with the sort of two data frames flipped around. But a right-hand join, you can just keep putting right in the same pipe. So that's the maybe why do we need a right-hand join answer.
All right, so once again, so the next code chunk, the one that you have now scrolled down to, shows you an example of how to do a right join, and this is identical to the left join. Everything's the same as the previous code chunk, except the object name is different because you don't want to overwrite the previous object, and instead of a left join function, we use a right join function. So we can execute that. And I would recommend, when you have some time, just to inspect the output of each of these joins and compare and contrast. Look at the just look at the top few rows. Look at the what goes in is in each of the rows, and also just look at the order of the columns. So that's a right join. Now the inner join is in some respects the simplest join, and it's the one that I use most frequently. Let's say you had a data set of, you had like a data set containing information on 100 proteins, and you wanted to join that to another data set that has information for 20,000 proteins. You could do a left join, but you would get a bunch of NAs for many of the rows. If you do an inner join, what it does is it only retains rows that are in both sets. So if you wanted relevant information for those proteins that are found in both data sets, you could do an inner join. And the output is a much smaller. So you see, this is unlike the previous two data sets. In this case, because the rows aren't perfectly matched, you get a smaller data frame output. So it's although you lose information, it's the output is smaller and easier to handle. So in this case, since it's just A and B that are common in the variable you're joining on, so in this case x1, those are the only two rows that are retained. Now C doesn't match D, so that row in both A and B is discarded. So once again, this is the text from the Tidyverse help page. And the inner join example, just like with the left join and right join, the syntax is the same. You just change the name of the function, and you change the name of the object you're assigning it to. So we hit that. And if you scroll back up to or you compare it to your PM right, PM left, look at the number of rows, you'll see differences. And I guess the most complete join is the full join, where you just take two data sets and it's like you join them together, or you just add them together. And it retains all the values, all the rows, and for the whether or no matches, you'll start to see a lot of NAs. So finally, this is the final code chunk we'll run for the joins. And again, syntax is identical to the previous ones. You just change the name of the join function you're using, and you change the name of the object you're assigning the output to. So yeah, so joins are a really useful way or effective way of taking two or more data sets and combining them. Now, if you have multiple data sets that all have common variables, you can't do a join on 3 data sets at the same time, so you'd have to do that sequentially. And since order matters for a lot of these joins, you'd have to beforehand work out the order in which you do it. But it's not particularly difficult or complicated. Yeah, that's importing and joining data sets. So if you have any questions, let me know. And as I said, this class doesn't have any homework assigned as such, but I would encourage you to repeat the joins and just change the order and see what you get.
Sometimes you'll have a case where the 2 data sets don't have anything in common, but
Yeah.
they might have something like entree gene ID that they both can be linked to, and then that makes them in common. Do you have to do the joins as multiple joins to first add the entree gene ID and then, or could you join by some intermediate characteristic?
So if I understand what you're saying, if you had some kind of a third data set that had the the relevant information, you could do one join to get for data set A, you could do a second join for data set B, and then you could join A to B. That would be one way of doing it. Sorry, I should repeat the questions. Paul's question was, if you don't have common variables, but there's a way to obtain a common variable, how would you do it? Thank you.
Okay, and if you look, I don't remember if I put it in the I think it's in the Tidybiology package. There is such a data set that can be used for such a purpose, Paul. Okay. Before we move on, any questions about importing data or?
Earlier is what are some of the differences between the data files? Like the differences between a CSV, a TSV, etc.
Sure. So the question is, what are the differences between some of the data files? So CSV is comma separated value. This is a format that is expecting a value and then a comma and the next value, and so on it goes. A tab separated value is expecting a tab in place of that comma. So really it's what the program is looking for to know to delineate one piece of information from the next. So like what you can do is you can actually open up like a text editor, and you can write a couple of words separated by a comma, a couple more words, and so on, and you can manually then save that as a comma separated value. If you reopen that in something like Excel or R or any program that can read comma separated values, it will interpret that as separate units of information based on where those commas are. So it's just a delineation method for the program to know where to separate those.
If I'm not mistaken, I think you can open CSVs and TSVs in like the text editor as well on Word or on your computer to see what it looks like.
Okay. Other questions? We won't go over it, but I thought I would just mention there's also a new clever little package called Vroom, VROOM, and this is a package that's very early in development, but this is a package that is importing data files, and what Vroom will do is it will very quickly load your data, but it will also guess the data type and guess what kinds of information are in that data. And so you can actually, if you're even lazier than read CSV or read TSV, you could just say room, and it will sort of quickly get loaded in. And so far, it either works perfectly or it completely breaks. So, but that's one thing that you can try. So, all right. Well, Allie's up with stringr.
Okay, so far we've looked at our data sets, we've plotted numbers, we've filtered numbers, looked at categorical variables, but now let's talk about characters. So the first thing I want you to do is open the lecture RMD, and I just want you to load your libraries and run the join function. It's the same join from Akshay's talk to create an object called mitoproteins that we're going to use for this part of the talk. This is where that little handy run all chunks before button comes in. Okay, so while you're doing that, you're going to create this object called mitoproteins. And if you take a glimpse at it, what you see is an output that looks like this. And you'll notice, for example, the first three variables are CHR, so that's character. So this makes sense to us as in there's no mitohomolog, there's no homolog, for example, or just mixtures of numbers and letters. And you see we have a few of these throughout the data. But these columns, importantly, they contain what's called a string. So this is something you've probably heard whether or not you realize it or not, but it's a character string, right? So a string of characters. So how do we work with those? And in this case, what we're going to use is a package cleverly called stringr. So stringr. So are people still working on making their mitoproteins object? Got it? Okay. So let's talk about how we can extract information from strings. So like I said, here are these strings that we have, and in the object you've made, you'll have a section called, it's your protein sequence, right? And that is a really long string of amino acid characters, right? What if we wanted to know how many characters are in that string? We can use a simple little function called string count. And all we have to do here is tell it our data in the string to be evaluated. So in this case, I've used our little $sign. So I say we're going to look at mitoprotein. I use the $sign to tell it to look at the sequence variable, right? So if you run this, it should be able to answer this question for you. So I believe it's in your lecture RMD, so go ahead and give it a go if you want. What it will output is a list. What is this list made out of? Anybody able to run it? If it's not in your lecture, you can just type it in. So anyone? What's the output? Numbers. So those numbers correspond to, yeah, the number of amino acids in this case, or more specifically to R, the number of characters within that string. So because these are amino acid sequence, we can say this is the length of the protein, right? Well, we can also get a little bit more specific with this. So this just...
Why doesn't it just generate a single column then, if you're looking at the sequence column?
Oh, because what it's outputting is not a data frame, it's a list.
If it did it all in a like a column, it would take up too much space. So that's
Yeah.
You think of it as a column, but it's doing it.
Yeah, it's just going across to show you as much as it can.
Yeah, and I'll just interject that if you ended up putting that, you might get into this, putting that in a mutate, you would then have a new column with all of the values for the corresponding string count that's right next to it. So it looks like it's just a big mess, but if you ended up saving that as an object, the type of object would be a vector.
Mm-hmm.
And it would be a vector of numbers separated by commas in this case.
Yeah. We'll talk a little bit more about mutating that in a moment. So we can get a little bit more specific with our questions in this case with a string. So this is string count, and as we said, it outputs a count, or the number of, in this case, characters in this string. But what if we only want to know something specific, like how many lysines are in each protein? So we can add a pattern for string count to look for. So in this case, it's a very simple pattern. We've put in string count, mitoproteins, $ sequence, and we're looking for K. And K is in quotations because, anyone? It's a character. I just want to hammer that home. So because these are character, we're looking at character sequences, we're going to be using a lot of quotation marks. Okay, so now if you run this, how do your numbers look different from the first run? Yeah, so they're a lot lower, and that's probably because your amino acid or your proteins are not made up of only lysines, right? Okay. So now let's get a little bit more complex and use the string count function to determine how many instances of lysine next to an arginine there are in your protein sequences. So I'll go ahead and let you give this a go.
Does anybody feel like that all of us have superpowers? You can push a green button.
Okay, so how do these numbers compare to how many lysines are in each protein?
Even smaller.
Even smaller.
How do you write in lysine next to arginine?
Okay, yeah. So how did anyone solve this? Was anyone able to successfully run it? Darren? What'd you do?
I just pressed the green.
Right, it's already there.
Oh, is it? Sorry. I spoiled it for you. My bad. So you just put the K next to the R. This is where reading ahead counts for something, right? Okay, so all I did was write an R right next to the lysine. Yeah, like Darren said, the numbers are even smaller. There's a few in the top there that are like 10 to 12.
But you said next to, does that imply K comes before R?
In this case, it does.
So you do
You
RK
can,
as well?
yeah, you can do the opposite as well. So that's just simply how to count the numbers of characters.
So if you separate them by like K and R, will it just give you the K and like all the lessons and arginines? Or you need to, it's just be enough, it must be just one.
I think you can only specify one pattern at a time.
You'd have to do 2 string counts for that.
I think so. You'd have to do 2 string counts.
Well,
Unless you are more
so
familiar.
ask the question again. What do you want to do?
I don't think that's practical to do, but I was curious if you can separate 2 characters and ask them to look for both together.
So you want to count the number of lysines and count the number of arginines independent of their location in the
Yeah,
sequence.
like
Yes.
2 characters.
There's probably
Do we have this open?
what the
String
no.
lecture.
There's probably some regex for it.
Yeah, so it would probably, I think it's going to look something like chunks above. So if we run this,
It's K.
that's K or R. No, that's not going to work.
No, they also have to. There's no spaces in that, I think, too.
You're right. Yeah, so if you do this, that's KR. If you do K alone, you get numbers like 11, 37, 89. If it's K or R, you get numbers that are larger. So this is the way that you would say, I want to know the number of lysines or the number of arginines. We'll talk about this in just a moment, but there is a way to say, I want this or this.
But it's not lysines, it's not like the number of lysines and the number of arginines separate, right?
Well, let's, we can actually look at that. We can go.
What? You can't, they can't see your screen.
Oh, okay, let's go like this.
Solid point in a moment.
Okay, so now you can see my screen. All right, so if we do this by itself, and we do this by itself, okay, and then we do this. Actually, let's go sum that and the sum of this. Okay, that should be the same as, oh, where did it go?
No, it's a single number.
No, but it should be able to take those two and add them together, right?
Yeah, but you scroll back down to where you were.
I'm trying to find where I am.
It just created a single number. Exercise 1. You were just right there. It summed them
yeah.
the way
No, you're
R
right.
sums.
No, but I think, yeah, we can, so I guess we can look at that more, but I think that this is the number of Ks or Rs in this.
But it's not like, it's not going to give you that output of there's this many lysines and this many arginines in this manner.
Yeah, because this says the first one has 11 lysines and it has 33 arginines and it has 44 lysines or arginines.
Mm-hmm.
Okay.
Yeah.
K and instead of K or
Yeah,
you do the same.
but that's,
So could you do KR, RK?
Yeah, so we'll get into more, so,
we're going to
yeah.
get into more complex.
There.
Okay. So, one important note here is while Matt was fiddling, I thought about it, but you guys couldn't actually see the screen. This character sequence, because it's a character sequence, remember that spaces count as characters. So if you had a space K space R, you will not get anything in return because we know that these characters don't have any spaces in them. So just know that this is a point where spacing matters. So this is simply how to count the number of characters or a character or the number of times your pattern appears. But we can also do logical evaluation with this. And this is a simple true or false evaluation, which means that your pattern is either present or absent from this character string. So to do this, we use a function called string detect. So, for example, you have a protein sequence. Let's say you want to look for a motif, right? Because this is something we commonly might find ourselves doing. In this case, I have the protein sequence for a heme regulatory motif. That is an arginine, lysine, or asparagine, followed by a cysteine, a proline, followed by either a lysine or any hydrophobic residue, and finally it finishes with either a lysine or a methionine. Okay? So we can use the string detect function to look for this pattern in our character string. So this is the similar setup as before. You notice we have our, sorry, this should say mitoprotein. I don't know why I did. So mitoprotein, we're going to look in the sequence column, so that's the string we're evaluating. And then this is the pattern we're looking for. So in this case, it's RCP period L. So what I want, for the sake of this example, we're going to say that part of our motif that could be a lysine or any hydrophobic residue, we're just going to accept anything in that space for now. Okay, so that's why I have an X there. So I want you to run the following code and ask yourself a few questions. How is this the same or different from string count? What does the period stand for in the code? And how does this compare to the sequence motif we actually are looking for? Okay, so go ahead and give that a go. Okay. So how is this the same or different from string count? Yeah, it's not a count. So what's your output look like?
Text.
Yeah, it's a text output of one of two options, right? It's a simple true or false. So true means what? Yes, it means the character string you're evaluating has the pattern you're looking for. It doesn't tell you how many. It just tells you that it's there. Okay? So does anyone think they figured out what the period stands for in the code? Anything. Correct. The period means we will accept any character in that position. And this I'll talk about a little bit more in just a second. So finally, how does this sequence actually compare to the motif we are looking for?
The R was variable. There was like 3 arginine, lysine.
Exactly. So Paul said there's variable points in this pattern, right? We will accept a couple of different options for the first position, and we have accepting any option at the 4th position, and then we could also accept a methionine at the final position. So once again, the period will accept any character in this position, right? And this is an example of what's called regex or regular expressions. So if you go to the stringr cheat sheet, on the back of it, I believe, is a list of regex. And these are not necessarily intuitive things, but it's a way to work with character strings and interrogate them and say, I want anything here, or I want this or that kind of thing. So we're going to use a little bit more of that as we go on. So they're a language used to describe patterns in strings. So then, as Paul said, this is not necessarily exactly what we're looking for. It's one of the options we would accept, but it's not what we're looking for. So how do we tell R that we'll accept different characters in those positions? So I'm going to start with the simplest one, which is the final position, where we'll accept a leucine or a methionine. So we're going to add more information to this pattern. So here you can see I've now added around our leucine, or our L, an open bracket, and I've put a line. So that line is the line right above your enter button. So there's above your enter button on your keyboard, there's a slash, and the if you use your shift button, you can get the line. That line is another example of regex, and in this case it means or. So our brackets indicate that within this one position. So we're going to say we have 4 things dictated for the first 4 positions of the pattern, but for that 5th position, we're going to put in a bracket and say, in this position, we will accept, and then tell it what we'll accept. So in this case, we put an L or an M. So this line means or, okay? So now that we know how to do that, go ahead and try altering the code to accept an arginine, lysine, or asparagine in the first position. So R, K, or N. this is first.
Riley, can you go back one slide? So the key right over here is
Oh, it doesn't have receipts. So you have to use strings. So
this is right here.
Sure.
C. That's almost like one first position. So X here just means equal, right? And you control that. The rest is here, these are
I'll give it another more minute and then we'll move on. Okay, cool. So, to accept either an R, K, or N in the first position, we're going to use the same logic we followed for that last position where we would accept an L or an M. So we create our brackets and we put the lines between the R, the K, or the N. So this tells R in that first position, you're going to look for any of these characters. And then you move to the next position, we will only accept a C. And in the next position, only a P. And then any character, and then in that final position, we would expect an L or an M. So, you got an output here, but string detect gives you a true-false output. So you can't actually check yourself, right? You just know that it says it's there. But if you want to check to see whether or not it's actually worked, you can use string view. So go ahead and replace string detect in your code with string view, and you can add the argument match to see what actually matches your pattern, and it will actually speed it up a little bit if you want. So go ahead and change this to string view, and once you get an output, somebody tell me what you see.
Protein sequences.
Yeah, so Paul's got it. Looks like a lot of us are still working. So I encourage you to add the argument match equals true, because if you run string view by itself on this code, it might take quite a few minutes, and it might be that's why I added the argument to my solution here, match equals true, because what this will do is only show you things that matched your pattern. So your output should look like this. Now, yours won't be yellow. They will be not very obvious gray boxes, but I've highlighted them in yellow here so you could see. But what you see, as Paul said, is the protein sequences. It shows you the whole character string, and then it highlights your pattern within that string. But we know our pattern is variable, so we can actually look to see whether or not our what we got back is variable, or if it's just all the exact same thing. So you can see in this first one, we have the RCPRL. In this third one, we have RCPFL. And here's one where we got RCPRM. Now, you'll notice that some of these have showed up and the sequences are listed, but there's nothing highlighted. That's because the whole sequence isn't here and the pattern is probably further down the sequence. I can tell you that we got things back that had K's or N's. It's just that in this view function, it's a little bit difficult to see.
Each line is one protein?
Yes, each line is one protein. You notice the fun part for proteins is they all start with methionines. You can see they all have our methionines here. But because these protein characters strings are so long that they don't all fit in your little window. Okay, so now you know how to count or detect your patterns in your string. But we probably want to assign something to our data set regarding this information. So if you have your data set and you're looking for a specific motif, you might want to assign a column that says true or false whether or not that motif is present. So we can actually use our string functions in conjunction with our dplyr functions. So here we have a code chunk. It's determining whether or not our motif is present or absent in our sequence. We know that because it uses string detect. And we want to add it to our data frame as a column. So here I've used the mutate function. I've told it in this protein data set, mitoprotein, that I want to create a new column called HRM motif for heme regulatory motif. And that's going to be equal to this string detect function, right? So then it's going to run that pattern search on the protein sequences and then create a new column that tells you whether or not that protein has the motif or not. So you can run this and go ahead and look at the new column you've created. So in your files, you also have a stringr homework document. I'm going to ask you to basically do the same thing. I've given you another motif you can search for, or you can go to the links I gave or the directions I gave to look for a different motif that might be more interesting to you, or maybe you just already know one. And go ahead and try in your homework to search your protein sequences for those motifs and see what you get.
So with that code, the mitoprotein is going to get re-saved as the new version?
Yes,
Because
in
of
this
that
code,
left
I'm.
code, because of that left thing.
Yes, in this code, you're right, Paul. I have I've created a new object, but it's going to overwrite my mitoprotein data set. But it's just going to add that column.
So when you view it, that column should be there.
Yes. So you should be able to do glimpse and see a variable named HRM motif, or just open your table and look at it. So, Paul, you were asking earlier about how to search for maybe extract information out of a column to use it to join, for example. So there are functions within stringr where you can extract patterns from a character string and only have that information in a new column. That's actually how I extracted phosphosites from my phosphoproteomics data.
Could you, like if it was GN equals, and you know every time it says GN equals, that's the G name?
Yeah,
Could
you
say
can.
take what's to the right of the GN equals?
Yeah, you can actually use your regex expressions to say, to tell it which parts to extract and which parts to leave behind. So.
Cool. So I did glimpse. I see that in chat.
Yes.
Yeah.
Maybe it's not already.
All right, one super sneaky thing that people are finding out right now is if we run this last line of code here. Oh, you guys still can't see it. Let me go like this. Okay. Then that should generate this new data frame, right? So if we run the first one, we can see to generate the file here, we can see we've got mito protein, which is 20,000 observations and 50 variables. If we run this last line, mutate makes a new column. So now we have 20,000 by 51. However, if you go to view, you scroll all the way over, you can see that there's 51 columns, but we're missing this last column. Some of you realize that. Well, it turns out view views 50 columns at a time. So if you click this to cruise over, then what you can see is now we're missing column number 1, but we get to see column 51, which is the one that we just made.
She's helping me with.
Yeah, so several of you sort of realized that. So, but now it's interesting because now we're just sort of freestyling. But we can do something like this. We can say mitoprotein, and then filter, and we just made something called HR motif equals true. Oh, equals true. And then what happens is we get a list of 205 rows. So that means out of all of our proteins, these are the ones that have true in this new motif, meaning they have this heme regulatory motif. So then we could maybe call this something special. We'd save this. Right now we've got a smaller data frame and we can go and do things with it. So this is a sort of workflow that you would do if you're interested in this sort of motif. So this is all that we planned for today. We have a few minutes. There's, Ali, did you mention the stringr homework?
Yes.
Oh, okay, so there's stringr homework here that Ali mentioned that you guys can hang out for a few minutes and work through if you'd like. Otherwise, go forth with your new superpowers and sort of play with regex all that you would like. The cheat sheet, I can tell you that I have a hard time doing anything in regex without the cheat sheet. So there's plenty of resources. James actually just showed me one, but there's plenty of resources online that will help you with regex if you're trying to figure out how to query a very specific thing. Then tomorrow, just a preview, tomorrow we will be wrapping up the formal lecture part of this by going back to R Markdown and showing you the power of knitting the R Markdown documents. So thank you for coming. Hang out if you'd like. Otherwise, we'll see you tomorrow.
Ben, would you mind putting that code you just entered back up there, the filtering for the HRL?
Yeah, it's right here. So the question was just to look at that code again. So there it all is.